Hello and welcome to section 7.4, Adding and Subtracting Rational Expressions. We're going to study this lesson over 2 days. In the first, we're going to be talking about just simply adding and subtracting rational expressions, and in the second day, we're going to be also rewriting and graphing rational functions, and we're going to try to simplify complex fractions. So to begin with, here is just a simple addition of two fractions to remind us of how the basics go so that when we get into dealing with the rationals, we'll have a better sense. We can take our two denominators and factor them so that we understand their components. A common denominator would be 4 times 6, 24, but it's not the least common denominator. To do that, we would need to take two 2's because there's two 2's in 4, and we would also need a 3 that's embedded in that 6. So to convert 3/4, we would multiply the numerator and denominator by 3. To convert 1/6, we'd multiply the numerator and denominator by 2. When we do that, we would come up with 9/12 and 2/12. Therefore, we're able to add, and when we do so, remember, we're just simply going to add the numerators to get 11, and 12 will be our denominator. Our first task is to add or subtract these rational expressions and state the domain, and can we explain why our answers are what they are. If you would like to pause these and do these on your own, if you would like to skip past and just check your answers at the end, that's probably a wise idea. For our first problem, 1 over x minus 1 plus 3 over x minus 1, our denominators are the same, so we should be in good shape to just simply say what is 1 plus 3 for the numerator, and we get our result. Remember, we can never divide by 0, so for this problem, our domain will be everything except for 1. If you plug a 1 in, we'll be dividing by 0, and that's undefined. For example B, we have x minus 1 and we have x in the denominator. In order to find a common denominator, we need to multiply those two things together. So our first fraction needs to have x over x multiplied, and our second one, x minus 1 over x minus 1. When we work to simplify that, we now have our denominator. We just simply need to say x plus x is going to be 2x, and we're going to subtract that 1. So 2x minus 1 for our numerator, and either x times x minus 1 for our denominator, or x squared minus x. Truth be told, we're probably going to stick with the first boxed answer first, because look at our domain. It's anything from 0 to 1. When we leave it in factored form, it's a little bit easier to discern that. When we go to example C, our denominators are x minus 2 and 2 minus x. Those are almost the same thing. And as a matter of fact, we can make them the same if we factor a negative out of the second fraction. Notice how that would work. We can now have 1 over x minus 2 minus 1 over x minus 2. When we subtract, we come up with 0 as our answer. However, if we're going to talk about a domain, we're still going to say that we have 2 being a restriction. We're not allowed to divide by 2. We're not allowed to divide by 0, so x can't equal 2. For the fourth example, we have x minus 1 and we have x plus 1. In order for us to get a common denominator, we're going to have to build up by multiplying those. So take the first fraction and multiply by x plus 1 over x plus 1. For the second, x minus 1 and x minus 1. When we distribute those 1's, we should have x plus 1 minus x plus 1. When we go to work that out, we're just left with 2 in the numerator. And again, either boxed answer is correct, but I think the first one helps us to see a little bit more clearly that both positive and negative 1 are not possible for our domain. For example E, notice that x plus 2 is equivalent to 2 plus x, so all we need to do are blend these together. Notice that we're subtracting now x plus 1, so that's going to be x minus x and also minus 1, so we wind up with just a negative 1 in the numerator, The only restriction on the domain is that x can't equal -2. For example, f, we have x minus 2 and x in the denominator. Our first fraction needs to be multiplied by x over x, and our second, x minus 2 over x minus 2. When we do that, it's going to require us to, first of all, multiply x times x and get x squared. When we FOIL x minus 2 and x plus 1, we're going to get x squared minus x minus 2. When we subtract those, the x's drop out. We're going to get a positive x and a positive 2. And I think leaving the denominator factored helps us to see that the domain can be anything except for 0 or positive 2. For example, g, our first fraction needs to be multiplied by x minus 1 over x minus 1, and our second, x plus 2 over x plus 2. Again, that's going to give us x squared minus x for our first term, and x squared and 2x in our second. When we subtract, the x squareds drop out, and we'll be left with negative 3x in the numerator, x plus 2 and x minus 1 in the denominator. Therefore, x can't equal -2 or positive 1. And finally, in example H, our denominators are the same, so we're ready to subtract. We just have to make sure that we are subtracting everything. So when I bulk them together there and in the numerator say minus parentheses x plus 1, it reminds me x minus x goes away, but it is 2 minus 1. Sometimes if we're not careful, we miss that the sign of that second value in the parentheses. So 1 over x, and x can be anything in the world except for 0. One of our fundamental thoughts when adding and subtracting fractions is that if we have like denominators, we simply add the numerators together or subtract them depending on the operation. Another key thing to note here is that c, the value in the denominator, cannot be equal to 0 because remember we can never divide by 0. So when we want to subtract 9 over 2x cubed minus 4 over 2x cubed, the denominators are the same, and we simply have 9 minus 4, and we wind up with 5 over 2x cubed. X can equal anything in the world except for 0 in this problem. In part B, when we want to add, again we have the same denominators, so we simply add together 4x plus 8. Those are not like terms, so we can't blend them together any better than that, over x minus 3. And remember, our domain here would be anything from negative infinity to 3, and from 3 to infinity. When adding or subtracting fractions with unlike denominators, we have to create a common denominator. In the first example, when we have a over c plus b over d, one way to create common denominators is simply to take that first fraction and multiply by d over d, and the second fraction and multiply by c over c. Therefore, our denominator is CD, and you can see that our numerator will be AD plus BC. It's essentially the same conversation to be had over with subtraction. But the note at the bottom here is reminding us that although this always works, it doesn't necessarily get us to the least common denominator. If you want to work with the smallest possible numbers, it might make sense in certain problems to simplify each individual fraction first and then decide how we can find the least common denominator as opposed to just a common denominator. Before we add or subtract fractions with unlike denominators, let's first work to find a common multiple, least common multiple. Can we find the least common multiple of these two trinomials, x squared plus 2x minus 8 and x squared minus 7x plus 10? That seems a little bit difficult at the moment. I think it might be easier to start off with an example with just some integers. 12 and 20. What's the least common multiple? It isn't 240. We could multiply 12 times 20 and say that both of those are multiples. 240 is a multiple of both 12 and 20,
but it's not the least common multiple. It's not the smallest value that they both multiply into. Instead, we can take 12 and say that that's 2 times 2 times 3, and we can take 20 and say that that's 2 times 2 times 5. If we want to know the smallest thing that they both multiply into, we need the 2, the 3, and the 5, and we need the greatest exponent, so that 2 squared. We need 2 squared plus times 3 times 5, and that would give us 60. That's the least common multiple. That's the smallest thing that they both multiply into. So now let's come back to our two trinomials. First of all, the x squared plus 2x minus 8. Do you see that that could factor into x plus 4 and x minus 2? And also, our second trinomial can factor into x minus 5 and x minus 2. So, similar to the example over on the left, we need all three of those binomial expressions, x plus 4, x minus 2, and x minus 5. That's the least common multiple of those two trinomials. And by the way, it's okay to leave it in factored form. Yes, we certainly could multiply all of that out. We could FOIL, we could distribute, we could collect like terms, but if you remember when we were graphing these functions with a binomial in the denominator, if we had something like x plus 4 in the denominator, you know that there was a vertical asymptote or maybe a hole at -4. If we leave this in factored form, if this is going to become our denominator, there's going to be points of discontinuity at -4, +2, and +5. If this happens to be in our numerator, we might have x-intercepts at -4, +2, and +5. So there's reason why we would want to multiply them together, but there's also good justification for leaving them in factored form. Now let's add with unlike denominators. You can see we have two fractions here. The denominators are not the same. They're color-coded for what's about to follow. I hope this will be helpful. The first thing we want to do is to factor each of those so that we can help determine what the least common denominator will be. So looking over on the left, I see that we can factor out a 3 and come up with x squared minus 4, and x squared minus 4 is a difference of squares. So just confirm that what was blue and what is now blue are equivalent to one another. And also in the second denominator, notice that we can factor out a 5. Okay, so now that we're looking at these, we have a 3, an x minus 2, and an x plus 2. And in the second one, 5 and x plus 2, both of those denominators have x plus 2 in them. So now we want to create a common denominator by multiplying. We want to build up the first denominator with what it doesn't have, and also the second with what it doesn't have. So the only thing that's missing on the left-hand side is that 5. We can't just multiply 5 in the denominator, we multiply it in the numerator also, because 5 over 5 is equivalent to 1. So when we do this multiplication, we're changing the look, but we're not changing the value of the expression. On the right-hand fraction, we have the 5 and the x plus 2, but we don't have the 3 or the x minus 2. So when we go to multiply by those, we now have a bigger, more complicated fraction for both, but at least the denominators are the same. Now, for the next step, we're going to multiply that purple 5 times the 2 minus 7x, and also the 3 times the x minus 2 multiplied with the x squared plus 4. I'm going to leave the denominator factored just the way you see it for the same reason as mentioned earlier. It helps us to recognize that there's points of discontinuity at plus and minus 2. What I might do is multiply by 3 times 5 to give us 15. So we get the 15 and the x minus 2 and x plus 2 in the denominator. 5 times 2 is 10. 5 times negative 7x is negative 35x. And for the second fraction, we get the exact same denominator, which is great. And when we take the time to FOIL the x squared plus 4 and the x minus 2, we should get x cubed minus 2x squared plus 4x minus 8. The 3 is still on the outside. The color coding is just for the sake of the next step, but if you can just make sure that that foiling made sense on the right. Now, in our final step, we should just be able to combine like terms, and that's why I had some green there, because we're going to have a negative 3x cubed. We're going to have 3 times negative 2x squared, so that's negative 6x squared. And then where did the 23x come from? We have negative 35x over on the left, and we have 3 times 4x, so 12x. When we perform that, we get negative 23x. We also have 10 over on the left, and 3 times negative 8, which is negative 24. Blend those together, and we get negative 14. So when all is said and done, we come up with that 4-term polynomial in the numerator, and I'd like to leave the denominator factored just to help us see if we were ever asked to graph this, we know that there would be points of discontinuity at negative and positive 2. Let's try another example of adding fractions with unlike denominators. This one is a little bit more difficult because there's 3 fractions as opposed to 2, but it's a little bit easier because each of the 3 fractions are already as simplified as can be. There's nothing to factor initially here. So our first step is to determine what should the least common denominator be, and then we're going to try to build it up. So our first fraction has 6x in the denominator, and our second has x squared. Notice there's at least one x in both of those. The third has x plus 4. When we go to create this, our first fraction, the denominator doesn't have 2 x's, so we need one of those x's from the second fraction, and it doesn't have the x plus 4. So we're multiplying by x and x plus 4 in both numerator and denominator. In the second, we have x squared, but we don't have the 6, and we don't have the x plus 4, so we multiply by those. In the third, we have the x plus 4, but not the 6 or the x squared. So you can see what the least common denominator is going to be. Now the numerators are a little bit messy, so we need to simplify each. Our first step, we're going to multiply all 3 expressions, x plus 3, x, and x plus 4. I personally would probably FOIL the 2 binomials and then distribute the x. For the second, I probably would do the same thing. I would multiply x minus 2 and x plus 4 together and then distribute the 6. And finally, for the third, I'd multiply 10 times 6 and x times x squared. Notice the denominators are all the same, and so we are now in position to add our numerators together. So we get 1x cubed, and way down on the back end, 60x cubed gives us 61x cubed. We have 7x squared and 6x squared. That should give us 13. We have 12x and 12x, which gets us to 24x. And we have the minus 48. Leave the denominator as 6x squared times x plus 4, and we are in good shape here. Now it's time to subtract with unlike denominators. When I look at these 2 fractions, I clearly recognize that the denominators aren't the same, but they're also rather big and cumbersome. I wonder if we can factor these and make them look a little bit nicer. So let's try that. For the first fraction, we can factor 2 out of the numerator, and the denominator is a difference of perfect squares, so that's going to give us x plus 3 in both the numerator and denominator. I love that. For the second fraction, we can pull a 7 out of the numerator, and after taking the 2 out, we're left with a trinomial that I hope is going to factor also. So with that done, with that stated, let's deal with that x plus 3 and x plus 3. And also I wonder about that trinomial in the denominator of the second fraction. Doesn't that fraction look so much nicer to deal with for the first? For the second, X squared plus 5x plus 4 simplifies to x plus 1 and x plus 4, and then we're in terrific shape again to knock out those x plus 1s. So simplifying leaves us with x minus 3 minus 7 over 2 times x plus 4. Okay, so we still don't have a common denominator, but it's much easier to deal with these three terms, x minus 3, the 2, and the x plus 4, as opposed to the difference of squares in that trinomial. So let's go and figure out what the least common denominator should be and build it up. The first fraction has x minus 3, but it doesn't have the 2 or the x plus 4, so we multiply it by those. For what it's worth, I'm leaving it as 2 times x plus 4 in the denominator, and I'm actually distributing in the numerator because we're going to distribute even further, multiplying by 2 in the next step, and we're also going to then combine with the second fraction. Our second fraction has the 2 and the x plus 4, but it doesn't have the x minus 3, so we have to multiply by that in both numerator and denominator. Let's now multiply in the numerator. 2 times 2x plus 8 should give us 4x plus 16. And 7 times x minus 3 should give us 7x minus 21. Notice that our denominators are the same. And notice that we're subtracting here. I know we said that from the outset, this is a subtraction problem. But I want to take the time to maybe do just one more step to try to avoid some rather simple mistakes. And that is, I want to distribute that minus sign so that we get a negative 7x or minus 7x and plus 21. When we see this fraction being subtracted with another fraction, it's almost never the case that anyone makes a mistake about minus 7x, but the 21 can be an issue. We're subtracting a negative 21, so we're in fact adding. Now we can combine like terms and see that we'll have negative 3x plus 37 over our denominator. We're going to pause 7.4 here. In day 1, we looked at adding and subtracting with like denominators. We found the least common multiple so that ultimately we could use it as the least common denominator when adding and subtracting unlike denominators. Tomorrow, or in our next lesson, we're going to rewrite and graph rational functions, and we're also going to work to simplify complex fractions. Looking forward to seeing you then.